13.8 billion years ago. Something happened that we still cannot fully describe. Space itself began. Time itself began. Every atom in your body, every grain of sand on every beach, every star in every galaxy, all of it, compressed into a single point smaller than anything you have ever imagined, suddenly began to expand. And it has not stopped expanding since. In the next 12 minutes, we walk back to the beginning of everything. Not the explosion, not the fireball, the actual moment cosmologists are willing to talk about, and the strange, deeper question of what came before. The answer involves a Belgian priest, a cosmic microwave whisper, and an idea so unsettling that even Einstein walked it back. In 1927, a Belgian Catholic priest and physicist named Georges Lemaitre published a paper that almost no one read. Working from Einstein's equations of general relativity, Lemaitre concluded that the universe should not be static. It should be expanding. 2 years later, Edwin Hubble would confirm this empirically by measuring the redshifts of distant galaxies. But Lemaitre had gotten there first, with mathematics alone. Lemaitre didn't stop there. He reasoned that if the universe is expanding now, it must have been smaller in the past. Smaller, denser, hotter. Run the clock backward far enough, and everything must converge to a single primordial point. He called it the primeval atom, a day without yesterday. The popular press, unsure what to make of it, eventually settled on a more colorful name, the Big Bang. The name was actually coined by the astronomer Fred Hoyle, who hated the idea. Hoyle preferred a steady-state universe, eternal, unchanging on the largest scales. He used Big Bang derisively on a 1949 BBC broadcast. The name stuck. The theory it mocked is now one of the most thoroughly tested ideas in the history of science. In 1965, 2 engineers at Bell Labs in Holmdel, New Jersey, were trying to use a giant horn-shaped antenna to measure faint radio signals. They kept finding a stubborn background hiss they could not eliminate. They cleaned the antenna. They scrubbed off pigeon droppings. The hiss remained, coming from every direction in the sky equally at the same temperature. Arno Penzias and Robert Wilson had accidentally detected the cosmic microwave background, the leftover heat from the universe's birth, stretched and cooled by 13.8 billion years of expansion, until it now glows at just 2.725 Kelvin in every direction. This was the prediction that the steady-state model could not make. The Big Bang model had predicted it precisely. Penzias and Wilson won the Nobel Prize in 1978. Fred Hoyle never accepted the result. In 1992, NASA's COBE satellite mapped the CMB in detail. In 2003, WMAP refined it. In 2013, ESA's Planck mission produced the most precise map ever made. From these tiny temperature fluctuations, variations of 1 part in 100,000, cosmologists have reconstructed the geometry, age, composition, and earliest seconds of the universe with stunning precision. What did the early universe actually look like? At 1 second after the beginning, it was a plasma at 10 billion degrees, dense enough that no atom could form. Photons could not travel freely. They bounced endlessly off charged particles, making the entire universe opaque. For the first 380,000 years, the cosmos was a glowing fog. Then, at 380,000 years, something extraordinary happened. The universe cooled enough, to around 3,000 Kelvin, for electrons to combine with protons and form neutral hydrogen atoms. Suddenly, light could travel freely. The fog cleared. The first photons set off across an expanding cosmos. Those are the photons we now detect as the cosmic microwave background. The CMB is, quite literally, a baby photograph of the universe, taken when it was less than a millionth of its current age. Then came the Dark Ages. For about 100 million years, the universe was filled with cooling neutral hydrogen, but no stars yet. Then, slowly, gravity pulled the densest regions of gas together until the first stars ignited. Colossal, hydrogen-burning giants, 100 to 300 times the mass of our sun. Their light pierced the darkness. Galaxies began to form. The universe we live in started to take shape. This is where physics, for the moment, ends. The Big Bang model accurately describes the universe from a tiny fraction of a second after the beginning. But the actual moment of beginning, what cosmologists call the singularity, is not a place where our equations work. General relativity says the universe converged to infinite density and infinite curvature, which is mathematics' polite way of saying we have no idea what happened. Two of our deepest theories, general relativity, which governs gravity and space-time, and quantum mechanics, which governs everything small, disagree at the singularity. To describe the actual first instant, we would need a unified theory of quantum gravity. We do not have one. String theory, loop quantum gravity, causal set theory, these are attempts. None have produced confirmed predictions. Some physicists, like Roger Penrose with his conformal cyclic cosmology, suggest the Big Bang was not really the beginning at all, that our universe emerged from the heat death of a previous one. Others, like Paul Steinhardt and Turok, propose cyclic models where universes collide and rebound. Still others, like Linde with eternal inflation, suggest our Big Bang was just one of many, one bubble in an endlessly inflating multiverse. None of these are confirmed. All are mathematically serious attempts to extend physics past the singularity. The Big Bang model has survived almost a century of brutal testing. Every prediction has held. The abundance of light elements, the geometry of space, the tiny ripples in the CMB that became the seeds of every galaxy we can see. We know, with extraordinary precision, what the universe looked like in its first second. What we do not know, what we may never know, is why there was a beginning at all, why the laws of physics are what they are, why anything exists rather than nothing. These are the questions that physics, at the moment, hands back to philosophy. Whether they will return to physics one day depends on whether quantum gravity, or something we have not imagined yet, can carry us past the singularity. The universe began 13.8 billion years ago. Or it didn't begin at all, and what we call the beginning was just a transition from a state we cannot yet describe. Either way, we are made of atoms that were forged in the first minutes, in the first stars, in supernovae older than our planet. The Big Bang is not just a theory of the cosmos. It is, in the most literal possible sense, the beginning of our own story. If you love careful, evidence-based exploration of the deepest questions in science, subscribe to Cosmic Edge. We never sensationalize. We follow the equations to where they get beautiful, and we are honest about where they end.